Russ was educated at Wesleyan and Harvard universities with PhD at the Harvard University in 1983. His professional experience is very rich, and let me name just a few positions. Professor Hemley, since 2019, holds the Liberal Arts and Sciences Distinguished Chair in the Natural Sciences and is Professor of Physics and Chemistry with appointment in Department of Earth and Environmental Sciences at the University of Illinois at Chicago. Russell was a research professor at the George Washington University, visiting professor at Cornell, also at the Carnegie Institution, Lawrence Livermore National Laboratory. He was director of several centers of excellence, including Energy Frontier Research in Extreme Environments, Department of Energy Frontier Research Center, director of the Geophysical Laboratory at the Carnegie Institution. Russ was also a member and later the chair of a very important and influential JSON advisory group, which is advising to the American politicians and generals. Professor Hemley was also visiting professor at the École Normale Supérieure Lyon, France, and at the Johns Hopkins University. Russ, since 2003, is also the director of the Chicago DOE Alliance Center, so-called abbreviated CDAC, which is a center of excellence for high-pressure science and technology. And he runs there a long, circa 150 seminars, series of excellent webinars. I'm participating myself in the seminars for quite a while, and really I can recommend them. Excellent lectures.
Professor Hemley is the world's leading scientist in the field of high-pressure physics and chemistry. His research interests include high-pressure behavior of materials, particularly Earth and planetary materials, transformations of hydrogen at multi-megabar pressures, novel high-pressure compound formation and pressure-induced chemical reactions in molecular systems, synthesis and characterization of new superhard materials, superconductors, and magnetic materials, pressure-induced amorphization, models for Earth and planetary interiors, development of high-pressure methods, and analytical techniques such as micro-optical spectroscopy, synchrotron infrared spectroscopy, synchrotron X-ray diffraction spectroscopy, laser heating, magnetic accessibility, electrical conductivity, high-pressure cryogenic methods, science issues related to national security.
And for decades, his research has pushed the frontiers of experimental science, enabling the exploration of matter pressures and temperatures one thought beyond reach. Among his many seminal contributions, particularly his work on hydrogen and hydrogen-rich materials stands out as particularly influential. His studies have addressed some of the most profound questions in condensed matter physics, including the nature of dense hydrogen and the search for new superconducting materials, while also impacting planetary science and material discovery. Equally important is his role as a scientific leader and mentor. He has been a central figure in building international collaborations and in shaping large-scale research efforts in extreme condition science, including large-scale facilities such as APS and ORNL.
For his pioneering contributions, his leadership, and his lasting influence on the scientific community, Russ has been awarded numerous prizes and awards. Let me name just a few of them: the Sack Lecturer at Cornell, the Marker Lecturer at Penn State, Pimentel Lecturer, University of California at Berkeley, Bridgman Award, International Association for Advancement of High Pressure Science and Technology, Honoris Causa Professor of the Russian Academy of Sciences, the Balzan Prize in Mineral Physics, Hildebrand Medal of American Chemical Society, Russ is also corresponding fellow of the Royal Society of Edinburgh, elected member of the National Academy of Sciences, fellow of American Academy of Arts and Sciences, fellow of American Geophysical Union, fellow of the American Physical Society, fellow of the Mineralogical Society of America, and he's even got a mineral, Hemley, named after him by some Italian mineralogist. Russ, the floor is yours. Thank you very much for accepting our invitation.
Well, thank you very much for that overly generous introduction. Can you see my slides okay?
Yes, we can see them, yeah.
Okay, very good. Well, thank you very much for inviting me to this very interesting webinar series on quantum crystallography and complementary fields. I think it's very appropriate to talk about this work on hot superconductivity, or our efforts to reach that in such a forum, because what I will describe really is a challenge, I think, to quantum crystallography. After all, we're dealing with hydrogen-rich materials, which are very quantum phenomena, and therefore will require new techniques to really do the kind of crystallography that we've been hearing about in this series. So my outline is shown here. I'll start with just the context of high pressure, then introduce some of these interesting phenomena in hydrogen-rich materials. Just a few examples. This is a growing field. Just a few examples in the binary, what we call superhydrides, turning to a couple of examples in ternaries, a few comments on related findings in other materials, and then conclude and with some comments on the outlook. So the themes I'd like to develop through this are really the synergy between theory and experiment. That's very important. The multiplicity of techniques that we need to use. We don't have the luxury of doing the kinds of elegant crystallography and scattering and other kinds of measurements you have at ambient conditions. So we need a number of different techniques, and therefore we also need very careful assessment of results. There have been continuing questions about what has been reported, but really there's an emerging consensus on a lot of the phenomena that I'll try to emphasize. But there are, of course, new challenges to experiment in theory, as I alluded to. We're interested in the pressure variable, and pressure is a remarkable variable that spans some 60 orders of magnitude in the visible universe. There on the left is a much wide range that includes the pressures of non-equilibrium gas in intergalactic space, hydrogen, to the kinds of pressures we have in a neutron star. The range of interest to us is a subset, but still spans many orders of magnitude, and this is the range over which condensed matter or chemistry evolves, and it's also the range of conditions that are relevant to the interiors of planets, including the many planets that are being discovered outside of our solar system. There's a table to convert among the different units that I'll be using. So let's start at the beginning and give a little bit of historical perspective. What happens when we compress atoms? The conventional picture was, shown in this simple model, is when you compress atoms, you reach a condition where you have no longer the electrons stable in orbits around the ions, and instead you have a distribution or a transition to a plasma state, a dense plasma state, and this arises essentially from the increase in the kinetic energy as you compress the atoms using a very simple density functional kind of idea, Thomas Fermi Dirac, shown here. But what this also shows is that chemistry is affected by this, and just as electrons around atoms are no longer stable at very high pressure, the electrons around the bonds that form molecules also get destabilized. And this goes back to a conjecture made exactly 100 years ago by Bernal, when he suggested that the ultimate state of all molecules is really a metallic or valence lattice. And this was in a footnote to a famous paper by Victor and Huntington that I will highlight. So let's think about this now in more modern terms. This was it was the conventional view for really, really many decades, going back a century, of course. But really, it's much more complicated and really much more interesting than this. We take an example here, and that's an example of a textbook metal like lithium. In fact, when you would compress it up to something like 1 million atmospheres of pressure or a megabar, what you find is something quite different. So you already have a metal, a plasma state effectively of the electrons, but in fact, you get localization of the electrons, you get a scrambling of the electron distribution, you get very complex structures. In fact, you can take these materials into semiconducting and even insulating states from metallic states, which is the reverse of this paradigm. What this means is we have a periodic table that really is a guide to how we think about the evolution of properties as a function of temperature and pressure and the chemistry that involves that is associated with this. But at the kinds of conditions we're talking about, many of those simple rules break down. We have altogether new structures, bonding, and properties across elements and compounds. And there are profound implications for creating new materials beyond the kinds of materials I'll be discussing, and also the prospect of really discovering new physical phenomena, certainly new chemical phenomena, but new physical phenomena. So let's just take one example of an important phenomenon, and that's superconductivity. Of course, this was discovered by Cameron Onus in 1911, where there's this resistance drop in mercury is now ambient pressure at about 4.2 Kelvin. And of course, the dream ever since this discovery was if we could increase the temperature range of this superconducting state in various materials, it would really revolutionize many technologies from the grid to transportation to computing and medicine. And it's interesting to note that there's the theory of superconductivity and the techniques that we're now using to study superconductivity in this very interesting new range of conditions really were born about the same time. This is the famous paper by Bardeen, Cooper, and Schrieffer. The BCS theory came out in 1957, and about the same time, the first proposed diamond cell apparatus was outlined in work done at the National Bureau of Standards here in the United States. So there's been an intermingling, a coevolution of superconductivity on the experimental and theoretical side, and the advancement of techniques for doing these high pressure experiments. So let's now look at some of the essential features of superconductivity, going back to the conventional theory, the BCS theory. You have the formation of Cooper pairs. In this theory, there's a coupling with lattice distortions, this would be enhanced. The TC that would be enhanced by the high phonon frequencies and a large density of states at the Fermi level. This is really the foundational idea, coupled with a gap in the system that gives you superconductivity. But there are also, of course, other properties that are connected to this: the magnetic properties, the suppression of superconductivity in a magnetic field, type 1 and type 2 superconductors, and the prospects of measuring other properties that are diagnostic of superconductivity, like imaging of vortices in a magnetic field. So the diamond cell was invented in the 1950s, and all the techniques that we're using for the kinds of experiments all describe, although we use other kinds of apparatus for other experiments based on the diamond anvil cell, where we have opposed anvils that compress a sample that's held in place by a metal shim that creates a sample chamber for the system, and a wide range of different designs have been produced. And what's notable, of course, is we're dealing with rather small devices with very small samples, because we're generating very high pressures at the very small tips of these diamond anvils. And a very important aspect of this is the technical side, that we now are able to do a lot of different kinds of measurements, not, of course, the number of measurements that we can do under ambient pressures, but we can do in situ synthesis with laser heating or various other kinds of heating. We can measure electrical transport by building circuits inside the diamond anvil cell. And we can also measure magnetic properties, such as magnetic susceptibility, by putting coils around our samples or putting our entire diamond anvil cell into very large magnets at large facilities. And this aspect of using large facilities is also very important because we're dealing with very small samples. So we need very powerful radiation facilities, such as synchrotron X-rays. And here's an example of the advanced photon source, which is just 30 minutes from me outside of Chicago. The National Synchrotron Light Source for X-rays. We also use this for infrared. There's also the importance of neutron scattering. Of course, this is quite important for quantum crystallography. We're not yet using this kind of technique at the kinds of pressures we're dealing with in these experiments, but we have preliminary results and been studying at lower pressures the systems with neutron scattering, also very large magnetic fields, and for very, very high pressures. I want to touch on this using other kinds of tools such as shockwave or ramp compression techniques. For example, it can be produced at, say, these very large laser facilities, such as the National Ignition Facility, which is the most energetic laser on the planet. So I mentioned this intermingling of pressure and superconductivity, and it's interesting to note that Kamerlingh Onus and his student actually were the first to study stress or pressure effects on TC, and some work done on tin and indium. And now we have the superconducting table of the elements. These are the elements that have been turned into superconductors or already superconductors at ambient condition, and really quite remarkable. 54 some elements are now known to be superconductors under some kind of high pressure conditions or ambient. And an important aspect of this also is just using pressure to tune superconductivity to maximize it. And this is was for many years the highest TC on record. This TC in this mercury barium cuprate material with a TC of about 164 Kelvin at 30 GPa. Our focus has been in this field in the last few years mainly on hydrogen-rich systems, and this dates back to this paper that I alluded to, paper by Wigner and Huntington, where in 1935 they predicted at some high pressure condition, and they set this as a lower bound, that it would be above some 25 GPa or 250 kilobars, and that would be the case in which you would destroy the the molecular bonds, as I pointed out in an earlier slide, and form some kind of dense structure, a plasma state, a metallic form of this abundant element, element 1. This was followed on by work by Neil Ashcroft some 30 years later, where he applied the BCS ideas, conventional superconductivity, and suggested that this hypothetical state of hydrogen could be a very high temperature superconductor, perhaps above room temperature. So a lot of work has been focused on this over the years on hydrogen. I won't describe any of the experimental results, but also a lot of theoretical results. Here is an expanded phase diagram. Note the log scale there on pressure, where we have the solid phase, we have the adiabats for these various planetary bodies and stars, including the sun. And then we have this regime at very high pressure above something like 400 to 500 GPa, where you have this hypothetical solid phase that could be a very high temperature superconductor in the solid state. There's some glimpses of this from experiments, but a lot of theoretical calculations are really converging on this regime as being what's required for the metallic or the superconducting state of hydrogen. But there are alternative proposals, predictions, and that is it may be not solid. It may exhibit some entirely new physics, and maybe a superconducting superfluid, a metallic superfluid, depending on the isotope in this range. So two different proposals for what one might find. This is a model or cartoon of the vortices of protons and electrons that one might be able to image. I showed an image of a cuprate vortices at ambient pressure, and this is what you might find if you could probe metallic superfluid or superconducting hydrogen at very high pressures. So along with this calculation that was done by Neil Ashcroft, he recognized there may be a need to look at lower pressure phenomena. This is a very high pressure for studying this material. So he suggested ways in which one might reduce the pressure of the insulator metal or insulator metal superconducting transition, for example, by destabilizing the molecular units in these structures, either by electron injection or with chemistry or a bias or with photochemistry, and this might reduce effectively the pressure of this transition in say a doped hydrogen system. And this was generalized to what he called hydrogen dominant metallic alloys, refined idea where the idea that chemical precompression might be able to stabilize what would essentially be the high pressure metallic form of hydrogen with chemistry, but at lower pressures. So this these calculations motivated a lot of work in the 80s and 90s, and we began working on this in the 90s and to develop the first techniques for doing studies of superconductivity in the elements, ultimately to look for some of these phenomena in the hydrogen-rich systems, and started with the elements. This was an early study where we used magnetic susceptibility to take sulfur from its insulating state to a metallic state, and found that it becomes superconducting at low temperature in its metallic phase at about 90 to 100 GPa, and it has this increase in TC with increasing pressure. So it has a nice TC of some 17 Kelvin at 160 GPa, which at the time was the highest TC for an element. Other elements were looked at by colleagues, for example, in Japan, found that gaseous oxygen, if you compress it, also becomes a superconductor, albeit a fairly low TC material, but roughly at the same kinds of pressures of 100 GPa, and it goes through very interesting intermediate states. In fact, these molecular structures emerge before it goes into this superconducting state. So this led to a series of studies that we carried out over the years, mixing different components together to look at the possibility of doping or using chemistry combined with high pressure to make this hypothetical material. And this led to the discovery of a series of new compounds, new classes of materials that we call van der Waals compounds, where one sees, due to molecular packing effects, altogether new structures. And this harkens back to what we heard in the previous talk. These are structures that are dictated by non-covalent interactions, basically van der Waals plus packing effects, to produce very interesting phases, very interesting materials that do not exist under ambient conditions. By mixing simple molecules, methane and hydrogen, for example, you can induce this kind of chemistry in xenon, water and hydrogen, and here is hydrogen sulfide and hydrogen. This was actually interesting because this is the precursor for the first high TC hydride superconductor that was discovered a few years later, and this was a precursor phase for that. So really what made this happen on both the experimental side and the computational side was the development of a structure search method. So we had all these ideas about where one might look for these high pressure phases that were in principle predicted or conjectured by Neil Ashcroft, but we didn't know which compositions, what pressure ranges to look for. And so these techniques that were developed, genetic algorithm techniques, were developed around 2000. A variety of different approaches were used, and this really also addressed the more broad question of the crystal structure problem that was articulated by John Maddox in a Nature paper, where he found it, or articulated, it's rather embarrassing that we simply cannot predict the crystal structures of materials at high pressure. In fact, this was proven wrong, and within a few years, we have a very good approach for doing this, at least for many classes of materials. So the development of these crystal structure search methods are very important. This is an example of just one by my colleague, Eva Zurek at Buffalo, University Buffalo. It's called the Extelop method. And you basically, because you have the ability with fast algorithms and large computers, you can search a vast amount of configuration space to find the lowest energy structures and explore this interesting energy landscape to find different structures, including metastable structures that could have very interesting properties. So these techniques were used to great success in the early 2010-2012 period, and a series of different structures were predicted. This includes structures of sulfur and hydrogen, tellurium, silicon, germanium, phosphorus and hydrogen, and others, including these lanthanides. The lanthanum H10 I'll mention because that was structure work that we did, or theoretical work that we did ourselves. And what emerged was actually a lot of these were quickly confirmed experimentally, the first being the SH3 or H3S, followed by our confirmation of our prediction of lanthanum H10. So just a few comments on that. This was the important work of the Michael Eremet's group, published in 2015, showing this beautiful structure here confirmed by X-ray diffraction and this very impressive TC of close to 200 Kelvin at very high pressure. Also the isotope shift that really is consistent with a conventional superconducting mechanism. So shortly thereafter, we focused on the lanthanides, and we focused on these because of the idea that they could in fact liberate their electrons and generate very high pressure superconductors with even more hydrogen present. All of these have atomic hydrogen in the structure, and this is the first measurement of the TC of this material, which is near room temperature with the highest TC of around 260 Kelvin. This was actually quite a challenging experiment, much more challenging than the work on H3S, because one had to synthesize the sample inside the diamond cell, measure X-ray diffraction, and at the same time on the sample without recovering it, measure some transport properties, for example, electrical conductivity or resistivity shown here. Another aspect of this, as I mentioned, that these papers confirmed these predictions, but the subsequent confirmation by experiments had been a problem. It took something like 5 years or 6 years for another group to confirm the results for H3S. In contrast, the Eremet's group confirmed within a few months of our announcement of this superconducting transition in this novel compound lanthanum H10 with very nice measurements, including additional magneto resistance measurements that support the superconductivity. So now a wide range of binary systems, binary hydrides have been studied, and basically the entire periodic table of binary hydrides and their TCs have been established theoretically, and for the most part where experiments have been done confirmed. So now we have a binary hydride superconducting periodic table here. And we have this plot here showing the maximum TC versus year, starting with mercury, going up through the cuprates that I mentioned, the iron-based unconventional superconductors, and now in this regime at very high temperatures, approaching room temperature, the hydride field. This is from a beautiful paper written by Warren Pickett, who laid out some of the ideas that really confirmed some of the early conjectures by Neil Ashcroft, that these are metallic hydrogen-like structures, and also the highest TCs occur near electronic and structural instabilities. And this is a very important point because they're near instabilities, one really needs to go to a higher level of theory to treat them accurately. And this is a great challenge to theoretical calculations, as I'll show. So the binary problem is, in a sense, more or less solved from the standpoint of just predictions of first order TC and showing quite high TC, the effects of magnetism and so on have been incorporated. Now in looking for going to higher pressures and looking for higher TCs, there's a focus on more complex systems. The first more complex system chemically would be the ternaries. And I turn to this quote from Bert Matthias, one of the leaders in superconductivity over the years, probably predicted and observed more superconductors, ambient conditions than any other scientist. And he, at the same time, was quite a naysayer when it came to room temperature superconductivity. He commented, room temperature superconductivity, regardless of 1,000 statements by theorists and an equal number of theories, is, in my opinion, pure science fiction. But he also wrote, a little bit later, shortly before he died, the field of ternary superconductors is still comparatively new, and there is still some hope. In fact, looking to ternaries, now going back to these structural search methods, some astonishing predictions have been made. In 2019, one of the groups doing these calculations for the hydride binaries predicted that this ternary lithium-doped magnesium hydride, that is electron-doped MgH16, in this particular high symmetry structure could have an astonishing TC of above 400 Kelvin. In the approximations that were made in those calculations in the high temperature, the hot superconducting regime. I was also a part of some calculations that predicted if we replace some of the lanthanums with scandium in lanthanum hydride, you find other structures and interesting stoichiometries, including this one with a TC around room temperature and a little bit above, around 300 GPa. So now I want to just turn to one example of some of the of a ternary system that we've looked at. This is these ternary systems in the hydrides have been the subject of a lot of studies over the years. I want to just show this one in part also to come back to maybe crystallography and structure work, because it shows the power of some of the newly upgraded high energy synchrotron sources. For example, the upgrade of APS, APSU, where we now have much, much tighter X-ray beams because of the change in the synchrotron lattice. And we applied this in some of the first experiments done at the APSU on this ternary, where we took some of the lanthanum out and replaced it with yttrium to try to lower the transition pressure and look at the effect of that lanthanum on the superconductivity. So we did resistance measurements using various kinds of techniques shown here. In fact, in particular, the one at the bottom. And as I described in the first studies, we did a combination of conductivity measurements and X-ray measurements. But now we can map in great detail with 1 micron resolution the structures that emerge. First of all, we have beautiful diffraction data now that we can take at quite high pressure. This is 150 GPa, somewhat lower than what was required for pure lanthanum. Beautiful patterns that we can refine. And interestingly enough, in this system, we're on the near a border between the FCC and the HCP structures, and we see 2 superconducting steps, a high TC and a lower TC. The lower TC is still quite high, 220 Kelvin. And the question is, which one is contributing, which structure is contributing to which superconducting step? Well, we can actually work that out by mapping out the structure and then correlating that with where we are measuring the resistance in these experiments. So this is a kind of resistive imaging that we're combining with the X-ray imaging. And we can see that when we have material and have conductivity, or we're measuring resistance between electrodes where we have a mixed phase, we see both steps. When we have what looks like the pure phase, we have the cubic phase, we have the high TC, so we can correlate the high TC phase with the cubic structure and the lower TC phase with the hexagonal structure. These techniques are also being combined with another kind of imaging technique that we're working on. This builds on proposals we made several years ago that you could use NV centers for Meissner effect imaging, and this has been developed and refined by several groups, including this group at Harvard, where they've done some of the first work at megabar pressures using Meissner effect imaging. So now we're doing experiments. We're trying to combine the spatial diffraction imaging, the resistance imaging, with the NV center Meissner effect imaging, all in the same samples at the same time. So I also want to come back to this prediction of lanthanum scandium-2 H24 and work done by our colleagues at Jilin University. They in fact have confirmed this prediction in a remarkable paper that's on the archive. Here we have the resistance data. They've done a number of different measurements, including magnetoresistance measurements. And what they see in a number of runs is a TC right around room temperature, albeit at somewhat higher pressures than the work on lanthanum pure lanthanum hydride, more like 260 to 200 or 250 GPa, but right around room temperature. So this is an exciting result. Again, a confirmation of the DFT predictions. So can we realize some of this remarkable behavior in hydrides near ambient pressure? Well, this is also a very active area of research in this field, and a lot of work has been done both theoretically and experimentally exploring this. I just want to take one example that we've focused on in the last couple of years, and that is looking again at the lanthanide series, but going from lanthanum over to lutetium, and following up on a remarkable report that appeared in Nature of room temperature superconductivity in a hydride of lutetium, measured with susceptibility and with resistance measurements, but at very low pressures, basically 2 orders of magnitude lower pressure than the superhydride work that I mentioned. The problem with this paper was it was retracted for a number of reasons, but we thought it was still worth studying this in detail because the data looked quite compelling. In fact, we did experiments on some of the same samples produced by that group as well as our own, and some of the first work we found, in fact, we could reproduce what was seen in terms of resistance drops as a function of pressure at quite low pressure. So here we have near room temperature and pressures in the range of 8 kilobars to 23 kilobars to GPa. We also followed up with magnetic susceptibility measurements, very much like what we pioneered for sulfur and other materials, showing the kind of signal you expect if you have, if you're at the onset of the transition in terms of the diamagnetism onset. And then if you plot the TCs, the resistance drops or the change in the susceptibility as a function of pressure, you get this dome, which very much matches what was seen in this report. And this generated quite a bit of excitement. In fact, it was on the front page of the New York Times, which delighted the 2 students who worked on this, both theoretically and experimentally. Has this been reproduced? Well, in fact, other groups have reproduced or seen something quite similar. This is work that's unpublished, again, from the General University group, showing similar kind of experiments with electrical leads attached to a sample at really low pressure. You can see this resistance drop on warming and cooling at quite high temperatures. The problem is, and this is what plagues the field for this system, and that we see this over and over again in our experiments, is you tend to see a decay of this behavior over time. So after multiple runs, the samples deteriorate, and that's one of the challenges in reproducing this. In fact, most of the samples don't show these resistance drops, but show something else. But there's still something quite interesting buried in this. There's another study, a very similar study that showed a magnetoresistance shift that's very similar to what you would expect in superconductivity. And here again, I show the results from our experiments. So this is work that's ongoing. It's very challenging. It's really a problem in chemistry and synthesis rather than a challenge for the transport measurements. But it's in a very accessible range because we're working at quite low pressures. How can we understand this theoretically? Well, apart from the superconductivity, these are very interesting systems, and this is something that one of my students who just finished this past year worked on. You can build up this structure of this trihydride-like system, a substoichiometric trihydride, in some cases with nitrogen doping, and for different orientations or different stacking of layers, you can make very, very interesting crystal structures with very interesting band structures. This is not the structure search method. This is more or less old-fashioned building a structure sort of with balls and sticks, but on a computer, and you can do a kind of band structure engineering. And what you find is that with the appropriate or ordering schemes, or you have all the nitrogens in this dope structure in the octahedral sites, you can produce a very, very sharp Van Hook singularity at the Fermi level. And I show here on the right that it's really quite sharp. It's much sharper than what we have in this. We do the same kinds of calculations for the superhydrides of yttrium and lanthanum, or for H3S. So there's a very, very interesting band structure in this material, apart from the superconductivity, but this is consistent with the superconductivity. And that's shown here. We now turn to real space and look at this structure here. And here we're plotting the integrated local density of states. What we find for this particular packing sequence or stacking sequence of layers is basically an embedded net of metallic hydrogen, where you have the hydrogens basically touching each other in atomic hydrogen. And this is characteristic of all of the superconducting hydride systems. And if you use various systematics to predict or estimate the TC based on this model, and this goes back to some work that was done by Belli and Aria several years ago using those techniques, you can estimate TCs that are quite high. Also, it has a very interesting Brillouin zone, which shows the flat bands and cones. So it's a very interesting topological material as well. Well, my student took this further and asked the question, well, can we replace lutetium with other elements, maybe combinations of elements to realize the same kind of phenomena at low pressure? And this is, again, a theoretical calculation. And what he recognized is that this structure that is proposed has a kind of core unit, an RH11 core. But if you start replacing the atoms in this core with non-lutetium, you can build very interesting structures going from 3, 4 to 6, 5 to 6 component hydrides. And all of these exhibit some of the same phenomena where you have this very sharp and intense Van Hoff singularity at the density of states. This is basically just, again, building a crystal structure model heuristically on a computer. Definitive predictions of structures and the TCs are going to require much more computational effort. So this is one of the great challenges for theory, is to actually turn these ideas into accurate predictions, as we had for the binaries several years ago. Another challenge to theory is actually looking more fundamentally at what's happening in these systems, because I mentioned these systems are highly quantum systems. Hydrogen is a quantum element, and there's kind of a quandary here in the fact that when we do calculations of the dynamics, what we find is something quite curious. Because of the highly quantum character and harmonicity in these systems, the materials that are highly diffusive with respect to the hydrogens, but we're using a harmonic approximation typically when we do the calculations of the TC. In fact, near TC for some of these systems, you have sublattice melting or partial melting. So it's very, very anharmonic, almost diffusive. So you have really now a new kind of superconductivity that maybe need to take into account this diffusive character of the material in these conditions where you also have very high temperature superconductivity. And this really goes to the fundamental, addressing the fundamental question of how do we understand this superconductivity beyond the conventional or even the traditional unconventional superconducting mechanisms. And on the question of unconventional superconductors, I just want to have a very brief mention of superconducting cuprates. Do we see some of these same phenomena under pressure now as we approach megabar pressures in cuprates? This is a compilation of TCs for various cuprates up to, say, 50 GPa, work done by another student. We have the mercury compound here, which has the highest TC of the cuprates, but we have these other cuprates. In fact, the bisco cuprates here, the structures are shown on the right, are very sensitive to hydrostatic stress, but you can, if you pressurize them carefully enough, you see this anomalous decrease and then a continued increase with pressure. He's been doing experiments extending this into the megabar range, and work he will present at the March meeting in a month or two. These are results now for TC for this particular cuprate, this bisco with some lead doping, and you see that there's a continued increase in TC with pressure. And the question is there a second superconducting dome, which is how we typically think about the superconductivity in these systems, and will it perhaps reach room temperature at the kinds of pressures we are able to reach with the hydrides? And this also takes us back to the famous Woodstock of physics, which was presided over by Neil Ashcroft, where he envisioned a future, a very bright future for high temperature superconductivity, and he was very much right. So some conclusions, we have an outlook. We have the original observation of superconductivity, which astonished the physics world back in 1911. The long sought goal of trying to realize this phenomena at higher temperatures and also ambient conditions. Our plot of superconducting TC versus time, the conventional superconductors, the cuprates, the peptides, and the iron-based, and then the regime now of the hydrides, which is in the vicinity and even possibly above room temperature. So the future is bright for continued discoveries in these and related materials. Again, as a result of the close synergy of experiment and theory and computation simulation, we still want to look for new phenomena, for example, in pure hydrogen, look for new materials, and the focus is really on complex chemistry to realize some of these phenomena. And just to conclude further, because this area has been somewhat controversial over the years in view of the really remarkable discoveries that have been made, this very nice commentary by a series of eminent solid-state physicists, experts in superconductivity, but not working in hydrides, and they wrote this very nice paper that came out exactly a year ago with the title "Hydride Superconductivity is Here to Stay." And so with that, I need to acknowledge a large number of people who contributed to this work, students and postdocs at UIC, leading groups of collaborators listed here, fellows at various facilities, and many others, including the people who make this work at those facilities, the beamline scientists, technicians, and so on. And also, I need to thank these agencies and institutions for financial support. Thank you very much.
Thank you for this excellent lecture and clear and exciting. While we are waiting for questions in the chat, I have a very maybe ignorant question. When you were showing the binary systems and your predictions, almost all elements were highlighted, but not carbon. Why?
Oh, actually, there is evidence for some of these same phenomena in pure carbon and disordered carbon. In fact, those are very difficult experiments and have not been very reproducible. But if you dope carbon in the same way that you dope some of these other systems, you can realize some of this very high TC superconductivity. You can dope carbon into hydrogen sulfide. But even in pure carbon, there are claims of quite remarkable behavior. There's signatures of superconductivity. There's no evidence for bulk superconductivity in those pure carbon systems at this point. And so it's somewhat controversial.
And my second question is, you mentioned electron diffraction at some point. Is it possible to combine electron diffraction with high pressure studies?
Yes, that is one thing that is quite difficult. So getting electrons in and out of a diamond anvil cell going through the anvils and windows of the sample make it extremely challenging. So you could potentially do a kind of ARPAS measurement or an electron excitation measurement with a combination of photo excitation, either with X-rays or optically, and electrodes. No one has done that yet. But the actual electron diffraction is really not possible. No one has done that yet.
Thank you. Krzysztof?
Before first questions and comments appear on chat, if you could comment, what is the quantum mechanical, I would say, fingerprint of superconductivity? Is this density of state, this maxima on the density of state you were showing, or what would you, how would you name this? A kind of, is there any fingerprint of superconductivity which could be clear suggestion that except resistivity drop.
Oh, well, there are a number of probes. I mean, for example, you need to prove the Meissner effect.
Yeah.
Not just the resistance drop. You can do geosystem tunneling experiments. You can do imaging of the vortices if it's a type 2 superconductor. So there are a lot of different tools you can use, and many of those can be done at high pressure.
From the point of view of quantum mechanics.
So from on the theoretical side, you need to look at some measure of the pairing of electrons. So you can look for a superconducting gap in the system, or multiple gaps, the anisotropy of the gap. It's not just the density of states. You have to look at the electron-phonon coupling at the Fermi level. So on the theoretical side, there are a number of different properties to look for.
But fortunately, all those systems are, I mean, the thermodynamic conditions, pressure and temperature, are such for some of those systems that we can do experimental studies and try to get electron densities or do this quantum crystallographic investigations of these systems.
Oh, you're looking for a signature in the charge density.
Is there any?
Yeah, that's a taller challenge for this, because in some cases you have a lot of electron density and you want to look for the signature of the Cooper pairs in that map of the density, and I think that's quite challenging.
Or you can use the same way of characterization as for theoretical, this NCI kind of analysis. You showed it on one of the slides when you were mentioned that you have this path of densities. So maybe that's something we can compute from electron density models fitted to experimental data. Yeah, but it would require exceptional high quality.
Yeah, well, one of the real challenges from the standpoint of quantum crystallography, I believe, is the hydrogen positions and the disorder and dynamics of the hydrogens. That's really one of the fundamental challenges, because it's a lot harder to do scattering experiments, diffraction experiments at these kinds of pressures where we see some of these phenomena. But we don't, in the case of the superhydrides, for example, we rely on systematics and theoretical calculations to identify the hydrogen sublattice. The hydrogen sublattice is not independently determined in any of the higher hydrides. So we know something about the atomic volume of the hydrogen, the pressure dependence of the atomic volume. So we use systematics to determine the stoichiometry and then compare that with what we predict theoretically. There's some spectroscopic probes, the optical probes, that can get a handle on that from vibrational spectroscopy, but that's somewhat indirect. But doing scattering experiments, first of all, diffraction experiments to identify the hydrogen sublattices in all of these systems, and then to do inelastic scattering to look at the dynamics of the hydrogen and now relate that to, or use that as a constraint on the mechanism of the superconductivity in these systems that are so highly quantum and anharmonic, is really kind of at the frontier.
So we have a question from Christian Jelsch, probably related to the carbon question. Something going on around graphene, like superconductivity related with graphene?
Well, you know, the observation of superconductivity in bilayers and trilayers of graphene and related 2D systems is relevant. Those are we think that some of the flat band physics that we see for example, in our theoretical calculations for the lutetium system are somewhat similar to what is seen in graphene. So we think that strong correlations may play a role, and it's a kind of unconventional superconductivity in those systems. I didn't get into that, but it may be different from or added onto the more or less conventional BCS idea that seems to explain the superconductivity in the higher hydrides. So some of those same phenomena that are seen in graphene or 2D systems in terms of correlations driving, strong correlations driving TC may in fact be quite relevant.
Thank you. A question from Sunak Sarkar. I may be wrong. There was an example of hydrogen crystal structure at 700 K, 500 gigapascal. How charge transport happens along C-axis between hydrogen layers? Is it similar to pi-pi transport, similar to charge transfer complex?
Well, in those conditions, you're deep into the metallic regime. So the electrons are all in the conduction band at 500 GPa. So it's a very good metal in those calculations.
Mm-hmm. A question from Mariama Hami. Hello, thank you for this important talk. Which superconductor types show the best promise for the next generation lossless power cables?
Well, we are particularly interested in continued studies of these lanthanides and the lower hydrides of the lanthanides, not the superhydrides, which have a lot of hydrogen. They're not as stable. They're not stable under ambient conditions. But the trihydrides and substoichiometric trihydrides and dihydrides, we think could be of the lanthanides, could be very could ultimately be the best system to deploy first once this technology is developed. It may require some degree of stabilization to keep the hydrogens in place, perhaps, but we're talking about pressures of maybe a few kilobars just to keep the samples robust and stable chemically and thermally in applications. So we're focusing on various lanthanides. There are also some transition metal hydrides that people are looking at, but most of this comes from more complex systems, not just the binaries, but maybe ternaries, quaternary systems.
Thank you. Question from Jarosław Majewski. Do we know anything about hydrogen dynamics in these compounds? You partially answered that.
Hydrogen dynamics?
Yes.
Yeah, well, what we know largely comes from these simulations. We can do quite sophisticated simulations of the dynamics and try to relate that to the superconductivity, and there are ways of doing that. There's still approximations that need to be made, and that's the point I tried to make at the end. When you do those simulations and go beyond the harmonic approximation in the simulations, you find the tendency for diffusive behavior, quantum effects, quantum diffusion, as well as classical diffusion in these systems. So that's largely from various simulations. And as I was trying to highlight earlier, one of the challenges experimentally is to see those effects, say, from inelastic neutron scattering or, say, inelastic X-ray scattering.
A question from Shabam Gavas. To what extent can the BCS theory explain superconductivity in cuprates and other high-temperature superconductors, and what are the limitations?
Yeah, the problem is BCS fails to capture the pairing in the unconventional superconductors like the cuprates, and you have competing effects of magnetism that play a role. So that's what defines the unconventional superconductors, is what is going beyond BCS. There's some more exotic mechanisms that have been proposed, but really it's when you have spins present, you can have pairing due to different mechanisms, not just electron-phonon coupling.
Nice. Anya?
Two small questions. So first one, perhaps also a bit ignorant. So at what stage the crystal structure is actually essential for superconductivity, and at what stage it actually becomes a secondary effect? It's no longer helpful. Can one say that?
The crystal structure?
Yes.
You mean periodicity?
Yes, for example.
Yeah. So to first order, you need to dissociate the molecular hydrogen. So the molecular hydrogen is stable. It's a very stable molecule, as you know, and when you put pressure on solid molecular hydrogen, it takes enormous pressure to dissociate it. And so, and when you have the pairing of the electrons are tied up in those bonds, and they're not free to contribute to the superconductivity. So in that sense, the crystal structure and the molecular bonding play a key role. So in the other systems, what was remarkable about the predictions of Ashcroft was that he found ways in which you could stabilize atomic hydrogen lattices by a combination of pressure and chemistry, where you have pressure ionization of a dopant, say in the case of lanthanum, it's the lanthanum losing its 3 electrons to this sublattice of a hydrogen net. And in that case, the hydrogen net, the hydrogen sublattice is crucial for the superconductivity. So crystal structure plays an enormous role here in controlling that.
And connected to that, are there some bonding motifs that consistently correlate, for example, with the high TC across the families of materials? Or can you
give
an example?
Yeah, that's exactly right. There are sort of 3 classes. One is the hydrogen cage structures, or the clathrate structures, which are really the same structures that you find in zeolites. They're not new structures. They're actually known structures. They're just new for hydrogen, and replacing aluminum and the silicon with hydrogen. And so there are those structures, and in those cases, the bond, the HH bond, is stretched well beyond what it wants to be, and that's really, in a sense, at the heart of the electron-phonon coupling, because you forced it to expand from, say, 0.74 angstroms to something like 1 angstrom. And so this tendency to want to pair gives rise to a huge change in electronic properties, and it's a phonon. So it's really, the electron-phonon coupling is tied to that. In the case of H3S, or those structures, you basically have an atomic hydrogen lattice, and you have the other elements, say in the case of sulfur, in a similar structure, and it's not a cage structure per se. But in the case of these newer trihydrides, it's still something else. And what we think is important is that they tend to form these flat bands. So that's why we think that in those systems, maybe the mechanism is slightly different, or there's an additional component. It's not due to the cages of the hydrogens or the kind of interstitial constitution of atoms in the case of H3S. It's something else. Does that help?
Yeah, absolutely.
Maybe following that from Jarosław Majewski, give us a little bit of intuition. Why lanthanides due to 4F electrons?
Yeah, it's interesting. Well, the yttrium and lanthanum are common in other superconductors, in the cuprates, for example, and they easily liberate their electrons. So those electrons, are able to take part in the superconductivity, and when you start adding F electrons, you actually introduce magnetism, and that tends to lower the TC. So it's really when you have a full shell of F electrons or no F electrons that you tend to see the most interesting high TCs in the lanthanide hydrides.
And another question from Supam Gavas: can topological superconductivity emerge under high pressure in layered hydrates? What experimental signatures? Topological superconductivity emerge under high pressure in layered hydrates. What experimental signatures would confirm it?
Well, yeah, there are people trying to look for that. I don't think it's been any topological superconductivity has yet been identified under pressure. There've been some proposals. You need to do other kinds of spectroscopy, for example, Andrea, reflection spectroscopy, to look for some of those phenomena. But that's an open question. I'm not aware of any convincing evidence for topological superconductivity in these systems.
Krzysztof?
Yes, we can see from the structures of ices studied by per distribution function that real structures are more complex. They are not that regular. They do not have that clear periodicity. And so hydrogens in ices, and water molecule, they occupy individual positions, but slightly off symmetry elements, etc. So I can imagine that in heavier metal hydrates, maybe we should go for another techniques to study their structures. I mean, real structures could be different from this periodic simple model we are getting from X-rays or from computations. So that I think it's we've done I7. You are showing I7 hydrogen, say, flat-rates. So we have to do this. We have to repeat this with the spread distribution studies, just to see this superconductivity in such systems.
Yeah, I agree. I think it's an open question. So
question from
we don't see by X-ray diffraction the hydrogens basically in most of these experiments. So we need to do that probably with neutron scattering, but we also need to take into account the kinds of effects that you just described that you see in the ices when you have, you're trying to pin down where the protons are. Exactly, I agree.
Another question from Jarosław Majewski: why not to go into 5F electron field? Dana Dattelbaum from LANL might be of help.
Oh yeah, I mean, there are predictions also for those as well, for those systems. So yeah, actually we work very closely with groups at Los Alamos on other problems, and they're studying, that group at Los Alamos has been studying superconductivity and actinides and so on for quite some time. So yeah, there are predictions of hydrides of those systems as well. We haven't gotten to that point yet.
As I do not see more questions or comments, let me just thank once again Professor Hemley for beautiful lectures.